So today I'm going to show you how to apply the drawings of molecules that you've been practicing to a new concept. We've drawn many different types of molecules. Remember, molecules are covalently bonded. You talked about the different shapes. You have linear and bent and trigonal pyramid and tetrahedral. And now we're going to look at some applications of this and how the structures of these molecules determine the types of functions they can serve and what types of things they can interact with. So today, the lesson is about how you determine if a molecule is polar or nonpolar. And this is very important. It's kind of unfortunate that the words polar and nonpolar are used to describe bonds, which we've already talked about, but they're also used to describe molecules. Any sort of question you'd be asked about something being polar or nonpolar, the question will be very specific. It will ask you if the bond is polar or nonpolar, or if the molecule is polar or nonpolar. And so there's two different sets of definitions. So this question, what is a polar covalent bond? That would be when you have two different nonmetals sharing electrons unequally, and that's because of different electronegativity values. And the more different the electronegativity values are, the more polar the bond is. Where a nonpolar covalent bond, that's when you have two of the same nonmetals sharing electrons equally because they have the same electronegativity value. So those are like your Brinkelhoff elements. So if you have two bromines sharing or two iodines sharing, etc. As long as it's the same two nonmetals that are attached to each other, that's considered a nonpolar covalent bond. So the first thing to cover is what molecular polarity is. So the first of all, molecular polarity is different than bond polarity. The type of bond it has is irrelevant. And again, the questions will be specific. A question will say, I will ask you if it's a bond is polar or nonpolar, or if a molecule is polar or nonpolar. So you just have to read carefully. So, just like bonds can be polar or nonpolar depending on who is bonded together, whether they are the same nonmetal, it's nonpolar, or different nonmetals, it's polar, molecules can also be polar or nonpolar. So for this, you have to look at the shape, which is why drawing these is so important. You also have to look at the distribution of electrons. Sometimes the shape is all you need to tell you if a molecule is polar or nonpolar, but sometimes you also have to address the elements that are involved and where their electrons are. So basically for this distribution of electrons, look and see if the bonds are exactly the same across the entire molecule. So if you're talking about a nonpolar molecule, nonpolar molecules are symmetrical. Two M's. Oops. They are symmetrical in shape. So just like in math class, if you have symmetry, that means that it's identical on both sides, identical on both sides. So here's several examples of nonpolar molecules. Carbon dioxide is a nonpolar molecule. This is one that I told you you could work through the method of drawing this, or you could just memorize the structure. So you could see that this molecule is symmetrical. It's exactly the same on both sides. Any diatomic element is also symmetrical. So if you have that bromine to bromine, it's exactly the same on both sides. So these shapes of these molecules, remember these shapes are called, if it's in a straight line, the shape is called linear. So if the molecule is in a straight line and it's exactly the same on both sides, it's a nonpolar molecule. CH4 is also a symmetrical molecule. If you were to draw out methane, I know I'm getting crowded here. If you were to draw out methane, it is symmetrical if I cut it both ways. So if I have a tetrahedron like this, that is exactly the same all the way around. Another example would be carbon tetrachloride. Exactly the same all the way around. Okay? If you have perfect symmetry for your molecule, it is symmetrical and nonpolar. A characteristic of nonpolar molecules is that they will dissolve in things that are nonpolar as well. And the rule that we like to apply here is that like dissolves like. So if I have a nonpolar substance, it will dissolve in a nonpolar molecule. An example of this would be oil-based paint. You can buy water-based paint, which is like latex paint, usually the stuff that you use in art class. You can also buy oil-based paint. You can clean your brushes in art class with water, and they clean up nicely. Oil-based paints you cannot, because the molecules that make up the paint are different. You have to use paint thinner or turpentine because the molecular polarity of the turpentine is similar to the molecular polarity of the paint. Another example of this is acetone. If you want to take nail polish off, you can't just wash your hands and wash it off. You have to dissolve it in something that is similar in its molecular shape. An acetone is a molecule that is similar in shape to nail polish. Acetone will also dissolve styrofoam because the molecule shape is similar. This is also why like oil and water don't mix, like why your salad dressing separates, because oil shapes are nonpolar and water shapes are not, or they are polar, I should say. So the opposite of a nonpolar molecule. So again, nonpolar is symmetrical. Polar molecules are asymmetrical in shape. So one example of this would be HCl. So if you were to draw an HCl molecule, its shape is linear. But because it's different on both sides, you do not have the symmetry that you would have in a regular like diatomic molecule where it's exactly reflected. So if you're asymmetrical in a straight line, you are polar. Water is also a polar molecule. You need to know the shape of a water molecule is bent. All bent molecules are polar and asymmetrical. Hydrogen sulfide is another one. Now, hydrogen sulfide is the same shape and arrangement as a water molecule, because if you take a look where oxygen is located on the periodic table and where sulfur is located on the periodic table, what do you notice about the two of them? They are located in the same group. And if they're in the same group, they have the same number of valence electrons, they have similar chemical properties, so they're going to bond similarly in molecules. Another type of molecule shape that is asymmetrical would be an example of ammonia. And you've drawn ammonia a bunch of times. This is definitely one you need to know how to draw as well. So you can see for ammonia, if I try to cut it in half across a vertical line of symmetry, it is symmetrical that way. But if I try to cut it in half across a horizontal line of symmetry, it is not. So this is an asymmetrical molecule. It's trigonal pyramid, and they are always polar. Third example would be the CH3Cl, which we did draw in an earlier lesson. So we put the carbon in the middle and we have 3 hydrogens around it, but then the fourth side is occupied by a chlorine. So this would be asymmetrical. Yes, it's a tetrahedron, but it's not the same all the way around, so it is asymmetrical and polar. So the rule for polar molecules is that polar molecules will dissolve other polar substances, like dissolves like. So because water is a polar molecule, it is bent. That's what makes water so such a universal solvent, because so many other things are also polar or have charged sides to them. It allows it to dissolve it. There's not a ton of nonpolar molecules. So in summary here, if you're not sure if a molecule is polar or nonpolar, draw it out. So here's another mnemonic device for you. We already talked about BARF at the beginning of this chapter. Now we have SNAP. So SNAP stands for symmetrical molecules are nonpolar and asymmetrical molecules are polar. Okay, so when you are talking about a polar or nonpolar bond, just look at who is bonded together. Are they the same? Nonpolar. Are they different? Polar. polar. If it's asking you about a polar or nonpolar molecule, it's SNAP. You have to know how to draw your molecule shapes in order to determine if they are symmetrical or not.